Well, guys, here's the absolutely amazing coincidence. You ready? I got an email over the weekend from the College Board, the people that own the AP test, and they have actually added an extra credit section to the AP test. Yeah, and simply all you have to do is figure out how to spell your name with elements.
I knew you were joking. Wait, and so cool. In California, on my final, we had extra credits. How many 5 or more letter words you can make?
I hope you know. I just got so excited because I knew how to spell.
I know. So, guys, removing our tongues from our cheeks. What we're about to do, and I know that you guys are horribly ill-prepared from this, hearing your belly, I'm tired, why don't we have break on Friday? So, guys, we are now going to launch into, the hardest thing we're going to do all year. Let's just call it what it is. So, we're going to do equilibrium. We're going to do this conceptually. Then we're going to do it mathematically. Those are 2 days, maybe 3. And when we do this mathematically, you are going to learn to solve problems. I don't know a better way to describe it. You're going to learn a problem-solving process that is actually going to be a more useful tool to you than dimensional analysis. So guys, think about how many times throughout this year you've been like, hey, I need to solve this. Dimensional analysis. Well, guys, the process that I'm going to teach you at the tail end of chapter 15, they're called ice boxes, are more important to equilibrium than dimensional analysis is to stoichiometry. This is big. The problem is that I have to teach all of this to you, and I'm now out of coffee. I know, this could bode well or poorly. But guys, the way that we're going to do this is we are actually going to start today by going back to the same demonstration that I did with you last year when you learned equilibrium last year. Matt right now is saying to himself, what demonstration? That's why we're doing this. So guys, yeah, and the thing that's interesting about this is for those of you that remember this demonstration, you may be having the same response that Catherine had of, I love this demonstration. This is actually really good. The thing that's cool about this demonstration, guys, is it gets even better given what you now understand about chemistry that you didn't understand previously. So for those of you that weren't here with us last year, you're now going, what's he doing? Well, let me show you. Yeah, and that's cool because you're making a connection that isn't immediately obvious, but is actually really important. So, guys, in order to get started with this conversation, let's make sure we're clear on what equilibrium is, and then we can start to doodle with this stuff together and play with some concepts. So, I would encourage you to, just as a starting point. So guys, what we're going to do today is we're going to explore the concept of equilibrium. We're not going to get into any of the math. But the cool thing is as we get into the concept of equilibrium, we can tie all this back to chapter 14. So now you're asking yourself, what does this have to do with chapter 14? Well, guys, if you write down these first couple thoughts, if you don't connect this back to chapter 14, you could be in trouble. So, what is chemical equilibrium? Well, guys, chemical equilibrium is this interesting condition that occurs when opposing reactions occur at equal rates. Do you get it? You get it? Guys, what does this have to do with chapter 14? Rates. Because everything that we did in chapter 14 was all about rate. And last year, when I did this demonstration for you, we simply said rate is the speed at which a reaction takes place. And that's true. But now, think of all the interesting conversations that we can have based upon the fact that reaction rate for you is no longer this meaningless concept like miles per hour in your car, right? That's not wrong, it's just not great. And now, guys, think about everything that you know about rate. You know about mechanisms. You know about rate determining steps. You know about rate laws. You know about reaction orders. You know about the rate of a reaction being dependent upon the concentration of reactants. You know, importantly, that reactions are always slowing down because reactions, by definition, are self-consuming systems. That as a reaction takes place, the concentration of the reactants is going down. Therefore, the speed of the reaction slows down. But interestingly, you also know that the rate of the reactions decrease is not always linear because we've got reaction orders, first, second, third order reactions. Because you know so much about reaction rate based upon everything that we did in chapter 14. Well, guys, guess what we can do now? We can take all of that information and we can apply it to this ridiculous graduated cylinder glass tube food coloring water demonstration. And the thing that's cool about this, guys, is it gets even better. That's the sign of a good analogy, a good parable, right? That a good analogy gets better as you dig into it deeper. And that's the beauty of this, is that actually when I showed this to you last year, it actually was even a little bit wrong. But we can fix it today. So guys, let's talk about how. Well, I think you're okay with this idea, right? So we understand that when we reach equilibrium, the rate at which the reactants form products is equal to the rate at which the products are turning back into reactants. That's essentially a retelling of the previous sentence. So guys, with that in mind, let's dig into this, and let's do that by doing this. And I want you to skip down like 3 lines, and I want you to write this big. Reactants in equilibrium with products. But guys, once you've done that, here's what I want you to do. I want you to write rate laws. I want you to write the rate law for the forward and reverse reaction. So guys, here's what we're going to do. We're going to go rate, and we're going to call this forward, and then we're going to go rate, and we're going to call this reverse. And guys, I want you to write the rate laws for these reactions. That's something you couldn't do last year. It's also something that's going to make this time much, much better. Some of you right now, as you're doing this, are thinking to yourself, is there really going to be extra credit on the AP test? You guys. Well, let's see how you did. You should be done. So guys, looking at what we are going to call rate sub F, which is the rate of the forward process, what does that rate law look like? So what comes first? K. But guys, let's be more specific. This is not just K, this is K sub F. This is the rate of the rate constant for the forward reaction. And then guys, what goes in the brackets? Reactants. Let's just call it R. Let's call it REACT. Just to make sure that we're not confusing R's with rates with whatever else. Okay. So now, guys, we can now figure out the rate law for the reverse process. So that's also going to be K. K what? Sub R. We'll talk in a minute. K sub R times the concentration of what? The products. So guys, our products are our reactants for the reverse process. Kind of a weird thought, but I trust it makes sense. But we have now written rate laws for both the forward and the reverse process. We okay with this? Okay, so guys, what I want to do before I dig into this with you is I'd like to talk with you really quickly about the significance of the fact that our K forward and K reverse are not the same. So notice, guys, and maybe I'd love it if you did this, but maybe you didn't. When you originally wrote your rate laws, I suspect some of you did not think to put subscripts on your rate constant, your K values. And guys, the idea here is that for most reactions, the K value for the forward and reverse reactions are not the same. So guys, let's remind ourselves quickly what K values represent. What do they represent? Right, they're the rate constants, but what determines the magnitude of those values? Temperature, surface area, things like that, right? That's sort of what we did last time. Well, guys, if you bring that idea together in your head, then maybe something like this would make sense. We talked about this previously, but if these are our reactants, and if these are our, let's say if this is our reactant and if this is our product, guys, we understand that the activation energy hump looks kind of like this, right? And we understand, I hope, that this activation energy can be influenced by the things that affect K. And so really, K is a representation of how hard that hump is to get over. Well, guys, why would K sub F and K sub R not have the same value? How are they different? Where do you see, right, keep going. Yeah, and that's represented by this, right? That this K sub reverse, and understand that activation energy and rate constants are not directly analogous with each other. But guys, the harder the hump is to get over, the bigger that K, or the smaller that K value will be. And so we would at least understand that the forward and reverse reactions would not have the same K values simply because the humps aren't the same height. Okay, so with that said, let's see if I can back out of this far enough. Now that's all the erasing I can do that way. So I'm going to have to do it this way. Okay, so with that said, is there anything you guys want to talk about before we start swapping water around? You guys okay? You're good? Okay, so guys, for those of you that haven't seen this demonstration before, I want to set the stage and then we will dig into this. And my marker is fading. I think it's going to be worth redrawing just so that you can see this better. So this is P for products. This will be R for reactants. Have you seen this before? This is good stuff. All right, so guys, when a reaction starts, how much reactant do we have? A lot, all of it, right? How much product do we have? We got none. Now, the thing that makes this, and again, in deference to those that haven't been here in the past, guys, what we're going to do is we are going to watch the blue water, which represents all of the matter that's taking place in this reaction. We are going to watch the reactant turn into product. But rather than simply pour the reactant into product like this, what we're going to do is we are going to allow, well, not allow, we are going to transfer the water using these tubes. And so I will be moving the water from reactant to product with this tube, and I will be moving the water from product back to reactant with this tube. And so we'll simply be passing the water back and forth like this. Does that make sense? Okay, now, the other thing that you need to understand to really fully grasp what we're going to be doing here is you need to understand that this tube, the one that we're going to allow to move the reactant to product, physically has a larger inside diameter than this tube. So you can actually even see that because one tube fits inside the other. So the forward moving tube will be like this, and then the reverse moving tube is smaller. You get the idea? Okay, so guys, what I'd like to do then is I'd like to give you a second now, and so Matt, I know, has anyone else other than Matt not seen this? A few of you. Okay, so guys, what I'd like to do, well, maybe I should be sure. Ethan, do you understand what we're going to do here? Does that make sense? That we're going to use this to move forward, and Matt, does that make sense? Yeah. Does that make sense what we're going to? So are we clear on the process? Okay, so what I'd like to do then, guys, is I'd like to step back from this a second and just give you a moment to process. Because what you're going to find out is, given everything that you learned in chapter 14, given the rate laws that you wrote on the board, and given your understanding of what we're about to do, there are some fascinating connections that you can make. So guys, before we get into this, given what you now understand, I'd like to give you a second to think through this, given what we're about to do, and connect how is what we're about to do tightly related to what we've written on the board. And I want to give people a second to think before we talk. If it's a question, wait on it. I just want to give you a minute to chew. So guys, how do these things connect? And if you're having a hard time knowing where to look at what's in red. Look at your rate laws. And guys, feel free to chat with each other about this. That's great. Hey, Brandon, I like that word. Don't lose that word. Ratio. Ooh, look at you, Mr. Smarty Pants. Good for you. That's the part we didn't get to talk about last year. You want me to heat up the water to make it go fast? Actually, I think what happens is as I heat up, the reaction goes faster. So guys, let's go for another 30 seconds and then let's play with this. Can we talk? So guys, we've got to get this off the table immediately. I was overhearing Isabel and Ethan talk about the idea of heating up the reaction to make it go fast. Okay, so maybe I was misinterpreting. We are not going to heat me up to make the reaction go faster. I know, see, I'm going to start sweating, and that would be bad. But guys, holy smokes, it was actually really cool to eavesdrop on your conversations, and Brandon's brain immediately is thinking about ratios. We're going to talk in a minute. The ratio thing here is even cooler than you know, unless you know and then you know how cool it is. So we're going to talk ratios and some really interesting ratios. But guys, I also heard you guys dissecting what's the water? What's the cylinders? I should be careful. What's the cylinders? What's the tubes? And I think you guys saw some really interesting connections. So what did you see? What's what? What's what? Interesting. Guys, did you pick up on this? The rate constants, and remember the rate constants are the small k's, right? Those are the tubes, not the cylinders. Those are the tubes. And I want to demonstrate to you how that's possible in just a second. But guys, these tubes represent the K values. Now imagine this. Imagine teaching general chemistry last year to you guys, when I had to do this demonstration with you, but I couldn't explain what the tubes were because last year you didn't know about K values. It's actually, it almost drives me to the point where I don't want to do this demonstration with general chemistry students because so much of this hinges upon the tubes. Do you remember what I lied to you last year and told you? I told you it was did I tell you a lot of stuff? Oh, I lie to you all the time. I mean, that's what makes a good general chemistry teacher, is being able to lie and not let on. But guys, seriously. But what did I tell you last year about the tubes? That's actually what I settled on. And I might have even used the word initial rate, that initially the forward rate is faster. Totally wrong. Guys, it's the K values. Now I'm starting to have like the cold sweats because I'm realizing I'm going to have to do this with my general chem kids. That you have to do this with 3 of them. So you've got to figure out how to explain this when we can't talk about K values. It's tough. But guys, okay, so the K values are the tubes. What are the cylinders? They are the concentrations. So guys, well, yes, but. So the water is analogous with the atoms. But when those atoms live in this tube, the higher the volume, the greater the concentration. So maybe that would be the better way to say it. Guys, volume is analogous with concentration. Does that make sense? So think about it this way. When a reaction starts, what's the concentration of reactants? A lot. What's the concentration of products? 0. There are none, and that's represented by an empty tube. So now, guys, this brings up an interesting third question. If the tubes, using my words carefully, if the tubes are K, and they are, and if the volume in the cylinder is the concentration, what then is the rate? What then is the rate? In the demonstration, what's the rate? Yes. Guys, it's this. It's the amount of water in the tube. Not in the cylinder. Be careful. It's the amount of water in the tube. So initially, we are moving a lot of water forward, which would indicate a high rate. And initially, we have no water to move backward, which would indicate a rate of 0. Now, guys, here's the thing that's really interesting about this. Looking, first of all, at our forward rate. Forward rate, quite literally, mathematically, is a product, right? It is a product of our K value times our reactant concentration. So take a look. What is our K value? Big. It's a big tube. What is our concentration of reactants? Big. It's a lot. And so, guys, what does multiplication look like in this process? It looks like this. This is literally what multiplication looks like. Multiply a high concentration times a big K value, and the product of that is a big rate. Does that make sense? Now watch this. What does multiplication look like over here? 0. K, good. It's K times 0. And K times 0 is 0 reverse, well, 0 reverse. Isn't that cool how that represents the multiplication? So guys, we got 0 product, so we have 0 reverse rate because there isn't anything in there for K to multiply times. But guys, we understand that reactions can't do math. So why is the reverse reaction 0? Because there's no product to turn in. There are no collisions because there ain't anything in there to collide. You get the idea? Okay, now guys, there's one more thing that, and I know Brandon, you're chomping at the bit, but hang tight. Guys, there's one more thing that I'd like to show you really quickly before we get started here. So let's disregard the fact that this process is reversible right now, and let's just focus on the forward reaction. So our rate forward is K, right, times the concentration of reactants, and what's now inside the tube? In the tube, rate. Big rate. Lots move forward. What about now? Less. So what is that representative of? The reaction slowing down, right? So as I do this, and guys, we could collect data, but the amount of water that I dropped the second time, representative of rate, was less than the amount of water I dropped the first time because the rate is going down. Now we understand that the rate is going down. Why? Concentrate, but that's not why. Why is the rate slowing down? Concentration is going down, but mathematically we see it this way. K doesn't change. It's a constant, but the concentration as represented by the amount of water in this tube is decreasing, and as a result, we see the rate going down. Does that make sense? Okay, so guys, this is actually a... Why don't I do this last unit? Remember that very first... Let me ask you this. If you cast yourself back to that very first day of this unit, Daniel, join me. Cast yourself back to the very first day in the unit when we said, what are the things that the rate of a reaction depends on? We said concentration, surface area, catalyst, temperature, that sort of stuff. And then we talked about, remember with the mason jars? And we talked about the idea that reactions are slowing down because the concentration goes down. Can you put yourself back there? Here's my question. If at that moment I had got out these two tubes, and if I had said, guys, this is why the reaction goes down, because when a reaction starts, we have a great concentration, so there's a lot to move forward. Understanding you don't even know about K values yet, right? But as the reaction goes on, there's less to move forward. Would that have been, but I really need you to go back and understand at this moment, you didn't know rate laws. You didn't know K. You didn't know any of that. Would that have, go ahead.
I think that it would help with that, but I also think that it did pretty much the same thing. And I think just looking at the mason jars was kind of like doing the same thing as this.
Right.
And I think right now this is more important because we understand K, we understand rate, and I think that it's like so much fun to explore right now.
Well, and so let me offer this then. I wasn't thinking about not doing the mason jars. I was thinking about doing this in addition to the mason jars. But what I'm wondering, and I'm not arguing, this is just the things teachers think about. If I had done this, given that it would have been redundant, I wonder if that might have not provided an easier connection to what we're doing now. Because 3 class periods ago, you would have seen this. Potentially, go ahead.
I think since it's pretty unique in how many layers the analogy has.
Yeah, right.
That also includes equilibrium, that at some point taking water from either cylinder will change the water level the same way.
Right, right. But understand, we wouldn't have gone there, right? We wouldn't have gone there 3 class periods ago.
I'm just saying, it's nice being able to see that, so I think
Right.
this equilibrium is kind of like rate plus something, and this analogy works for equilibrium as well.
Yeah.
So I think now is a good
Yeah, okay. So maybe what I'll do next year is, based on all of your input, I wouldn't drop the mason jars, but maybe add this as a reinforcer, and maybe it'll make a better connection. Okay. Where did Austin go? Oh, wait. Catherine, where did Austin go? The bathroom. Oh, it was brown. Okay. All right. So, guys, are we ready to now do this? Okay. So, guys, in review, Brandon, here we go. In review, what does the amount of water in the tube represent? Concentration. What does the tube represent? K. What does the amount of water in the tube represent? Oh, boy. Here we go. So guys, when the reaction starts, we have a lot of reactant and therefore a high forward rate. You will then notice that we had no product and therefore no reverse rate, right? Okay, now as we continue, what just happened to our forward rate? Got smaller. Why? Concentration went down. But now you'll notice we have a reverse rate. The reverse rate is relatively small. Why? Don't have much product. But we do now have a rate because we're no longer multiplying by 0. Again, the idea is chemical reactions can't do math. So why do we actually have a reverse rate? There's some products to collide. Let's call it collide. And so now reactants are turning into products. Products are turning into reactants. But now, guys, watch. Let's connect the dots. What is happening to the amount of reactant? Going down. What is happening to the forward rate? Going down. What is happening to the amount of product? Going up. What is happening to the reverse rate? Going up. And as we continue, reactant turns into product, and product turns into reactant. And unfortunately, there's no real mystery in terms of what's going to happen because you guys saw this happen last year. Frighteningly, some of you may actually even remember the ratio. It is 70-30. It's scary you guys knew that. But guys, eventually what's going to end up happening if I continue to do this is going to settle in at a 70-30 point where we're going to have 70 milliliters, 70 concentration units of product, and we're going to have 30 concentration units of reactant. And guys, we're actually there now. We're at that 70-30. And so guys, now that we've hit that 70-30, look at what's going on. How much reactant do we have? Not much, but we have a large K value. So a small concentration of reactant times a large K value is then being offset by a small K value times a large product concentration. What are you doing? Times a large product concentration. So guys, check this out. Small concentration, big value of K. Large concentration, small value of K. And when we multiply those two things together, what do we know about the amounts of water in the tubes? They're the same. Representative of what? Representative of equal rates at equilibrium. And guys, that's the idea that we have now. I'm going to make you wait for a long time. Guys, that is now the magic of this, because we have a small K value, or a large K value times a small concentration, a large concentration times a small K value, and those products are equal at equilibrium. Now, here's the thing that I'd like to explore with you. This, and I know that you've got questions. I've already told Daniel I'm going to make him wait. I'm going to make you all wait. Watch this. Guys, this settled out at 70-30, right? The question is why. So guys, check this out with me. We're going to do some math together. Are you all settled on the idea that we're at equilibrium? Now let's answer this question. What is equal at equilibrium? The forward and reverse rates. You good on that? Now guys, let's talk about why this settled out at 70-30. So join me at the board and let's do some math together. Okay, so what is equal at equilibrium? The rates. So these are the same. You okay with that? So if those are equal, what about those? They are also equal. Does that make sense? This only works at equilibrium, but if at equilibrium these are equal, so are these. So you ready to figure out where the 70-30 ratio came from? Guys, check this out. You're convinced that these are equal, so here's what we're going to do. If these are equal, we're going to set these equal. So do this with me, and I'm going to write up high so you can see. So we're going to go K sub F times the concentration of reactants is equal to K sub R times the concentration of products. Now here's what I want you to do. Solve this for products divided by reactants. Solve this for products divided by reactants. So guys, check this out. If we solve this for products divided by reactants, I am going to divide both sides by reactants, and that cancels. But now to solve this for products divided by reactants, what do I have to do now? Divide by K sub R. And now here's what we get. K sub F divided by K sub R is equal to product divided by reactant ratios. So now guys, watch. Remember that 70-30 ratio that we talked about? Where is that on the screen in blue? On the right? It's right there, right? 70 divided by 30. The amount of water in the tubes represents the concentration. Our concentration ratio is 70 divided by 30. Why? Given what you now understand, why is that? What made this 70 divided by 30? Go ahead. Exactly. The ratios of K. And what was analogous to the K values? The diameters of the tubes. So guys, what determines the equilibrium mixture when a reaction reaches equilibrium? I don't ask that rhetorically. What determines the concentration ratios at equilibrium? The value, yes, the ratio of the rate constants. You remember, Brandon, when you said ratio and I got excited? That's why. Because, guys, we can now talk about why 70-30. And the answer is because there's something about the size of these tubes that is a 7-to-3 ratio. So the ratio of your K values will also be the ratio of your product reactant concentration ratios. Now, guys, for those, and this is where we're going to end today. Guys, for those of you that are really tuned into what we did last year, switching colors again, does that look familiar? A product divided by concentration ratio, Kc. Guys, this last year we called Kc. Remember, Kc is the concentration of the products divided by the concentration of the reactants. Guys, now we have another way to approach Kc. In order to figure out the Kc value, which is the product divided by concentration ratio, or reactant ratio, that Kc value, 7/3, is determined by the ratio of the rate constants for the forward and reverse reaction. Interesting, right? I find it interesting. So, guys, grab your books then, and let's sort of have this moment. If you grab your books and open up to the beginning of chapter 15, actually, let's be more specific. Guys, open up to page 613. Guys, take a look at, you understand this, right? The equations within the writing of the text are denoted by 15.1, 15.2, 15.3. So guys, look at 15.4. We are looking at a completely different reaction. You can read more about it later. But the idea here, guys, is that we wrote the rate expression, the rate law for the forward and reverse reaction. That's 15.4. Then, guys, what allowed us to put them equal to each other? Why is it they're saying the forward reaction and the reverse reaction are equal to each other? They're at equilibrium. because those are both rate laws. And when are rate laws equivalent for forward and reverse reactions? At equilibrium. And notice what they did. They solved for the concentration of products divided by the concentration of reactants, and that's equal to Kf divided by K sub r, and that's equal to a constant. But what do we know that constant to be? K sub c, right? But guys, understand that this K is a big K. It's not a little k, it's an equilibrium constant. You okay? Yeah. Guys, it's K sub c. And that's equal to products divided by reactants. You get the idea? So, guys, this just got better, right? I think you probably understand not just equilibrium, but also rate and rate laws and concentrations and the effective K values and all of that stuff, and even the multiplication that results in rate. Again, mathematically, not what really is going on. But guys, in a way that you probably didn't understand before. So functionally, guys, what we did in the last hour is we just did page 613. This is why teachers get paid the big bucks. Because, guys, in college, your professor says, read it. In high school, we go teach it, right? Because, guys, it took us an hour to really wrap our mental arms around what the book covers literally in half a paragraph, right? You guys would have read, when you read over this as you were summarizing chapter 15, I suspect that barely caught your attention. That's the thing that makes learning from a book, Daniel, I'm going to kill you. That's what makes learning from a book so stinking difficult is, guys, this stuff is so rich. And if you just skim it, the details are lost. But that's understandable because there's no way you would have looked at that and going, man, oh, that's just like the water thingy, right? Unless you're Isabel. But guys, seriously, that's sort of the challenge of all of this. So we're going to stop there. The problem is this. That leaves us with most of the conceptual stuff to build on from, and it's not a problem. But this is the problem. Here's your homework. No, the problem is figuring out which ones you can do. Yeah, because we haven't even got through 5.1 as far as the 15.1 as far as the chapter goes. Well, we've started into 15.1. Hey, 1 through 10. 13, well, you guys can write. But guys, here's what we're going to do. On Thursday, I would like to talk about the small portion of this that you can actually do. But you're going to have to be careful about not getting ahead of yourself. Then we will finish this conversation about the concepts of equilibrium. We'll finish that Thursday. Then, guys, Monday will be the math of equilibrium. Wednesday will be a wrap-up day, including Le Chatelier's principle. Friday, however, will not be your test. What I want to do, because we've got that test we took before Christmas break, right? I'm not sure when this is going to happen, but we are going to insert a day. Actually, I do know when it's going to happen. Guys, what we're going to do is Thursday, we're going to finish up this conceptual stuff. Then when I see you on Monday, we're going to rewrite the last test. Okay, we'll do it in class. Then Wednesday will be the math of equilibrium. Friday will be our wrap-up day with Le Chatelier's principle. And then Tuesday of the next week will be our test. Does that make sense? Okay, so guys, we've got 4 minutes left. Daniel, I'm not ready to go there with you yet. I'm still trying to figure out why you're not paying attention to me when I'm trying to help you. So we'll talk later. So guys, we've got 4 minutes left. Let's wrap up there, and we'll come back. And then, guys, we are going to delve into lab and see if we can keep from hurting ourselves building our lab setups. We should.